My name is Chris van Hoof from IMEC, OnePlanet and University of Leuven, and I will tell you about innovations that enable Industry 5.0 in the domains of agriculture, food and health. The terminology Industry 1, 2, 3, 4, 5.0 is being used to describe increasing roles of technology in industrial production processes. And while Industry 3.0 is definitely mainstream today, Industry 4.0, meaning the use of cyber physical systems and IoT devices, is not yet universally applied, particularly in sectors such as food, agriculture, and healthcare. Neither is Industry 5.0, which adds more human-centric cyber-physical systems, which adds cognitive systems and brings customization. Obviously, later on, we can anticipate there will be an Industry 6.0 emerging that will rely for sure, among others, on generative AI. The timelines over the last 2 centuries since the start of the Industrial Revolution are shown here. And there is only one catch. The starting dates may be correct, but the end dates of Industry 3.0 and 4.0 are a bit on the optimistic side. Those technologies are still being applied and being used and developed. To make, however, Industry 4.0 and 5.0 a reality, chip technology is seen as the core enabler. As you know, chip technology has brought us all kinds of innovations that today we take for granted in terms of computation, seamless communication, also in terms of automotive driver assistance systems, in terms of cloud AI and edge AI, and for sure, it will enable personalized medicine as well, all building on chip innovations and Moore's law. Now, while chip innovation is a core enabler, we have to keep in mind there is a lot of leverage from the chip to the system to the product in terms of value creation. Every euro spent on semiconductor R&D yields more than 90 times as much, 90 euros of market value. Now, even though there may be clear value creation and economic impact, you may still wonder why Industry 5.0 is so important in the fields of agriculture, food, and health. Why is it important, and why do we even absolutely need to enable it? The answer lies in the massive global worldwide challenges. After all, how will we be able to feed 10 billion people in a sustainable manner in 2050? How will we keep people healthy? How will we reduce our impact on the environment? These are massive challenges. And addressing these challenges is also a massive opportunity, which will lead to economic growth and competitiveness. Now, with these challenges and opportunities in mind, OnePlanet Research Center was created 6 years ago in the Netherlands, in the province of Gelderland, supported by the province. Now, OnePlanet Research Center is an interdisciplinary collaboration of the Global Technology Innovation Center, IMEC, and 2 key universities in the region, Wageningen University and Research, and Radboud University and Radboud Medical Center. As an innovation center, OnePlanet focuses on grand challenges in health, in food, in agriculture, and environment. And we do so with the aim to achieve both economic and societal impact. And we build on chip technology and AI innovations for solutions that we create together with partners, with customers, with worldwide academic colleagues. And we build for sure on the know-how and strength of these founding partners. And while our team currently has about 100 people, with 100 people you can achieve a number of innovations, yet we can rely on the skills and strength of the 20,000 people from our founding partners. That magnifies our impact significantly. Now, our innovations take place at the intersections of agriculture, food, nutrition, health, and medicine and high tech. And the focus is on making Industry 5.0 and, where needed, Industry 4.0 a reality. Now, let me start with Food 5.0 and Food 4.0. Why is this so important? Well, the answer lies, among others, in the massive amount of food waste and food loss. You see that here on the slide, over 30% of food is lost, and food production is responsible for almost 15% of global warming. And to make matters more complicated, food loss varies across produce, as you can see here. It can be as high as 65%, and the losses vary across the value chain as well, as you see here. There are losses farm and field, during post-harvest, during food processing, distribution, and a large amount of loss during consumption. This complicates matters too. Losses are very well controlled in distribution, for example, because that's more centralized. Tackling the behavior and the loss at the consumer side is a big challenge. And these are exactly the reasons why Industry 4.0 and 5.0 solutions are needed in these multiple areas. To make it even more complicated, there is a large diversity in requirements. That means you need very different types of sensors and IoT devices and multiple sensing concepts. Imaging is needed for sure, spectroscopy is needed, so a number of optical techniques are essential, yet also chemical sensing, biochemical sensing, structural, mechanical, morphological, all need to be determined. This complicates creating solutions for Industry 4.0 and 5.0. Apart from tackling food waste, which will have a large impact on these global challenges, the protein transition is an important yet disruptive additional change. And the aim of the protein transition is to have both a positive environmental impact as well as a more sustainable food production for a growing population. Now, moving from animal protein to non-animal protein is a challenge also on the behavior side, but definitely on the product side. And as you can see, production of animal protein, and particularly beef, has a large impact on our environment. So we can solve many problems at once if we move from animal-based proteins to other sources. Now, which are those sources? You see them here. They can be plant-based, they can be insect-based, they can also be based on vat-grown meat, cultured meat, and a whole set of alternative sources of protein are based on fermentation, on bioreactors, relying on bacteria, on yeast, on fungi, or microalgae. Microalgae are particularly appealing because they are rich in carbohydrates and are one of the most sustainable sources of alternative proteins. Now, such bioreactors need closed-loop process control. And to assess or control nutrients, to measure functionality, to measure protein quantity and quality, and to measure food safety. And all those ingredients are needed to come to a closed loop system. Here you see an example of such a photobioreactor. And if we can indeed fully inline control the growth conditions, we can truly optimally steer production, minimize losses, improve quality. And in the framework of a multi-partner collaborative project, we work towards a circular economy by combining greenhouse agriculture and microalgae production. How do we do that? Well, the effluent of the production of vegetables in the greenhouse is still full of nutrients, and they can be used to cultivate microalgae. That biomass can later be processed for feed, for aquaculture, or to produce biofertilizers and circle back towards the greenhouse. Really an example of circular economy. And to make this possible, we focus particularly on this photobioreactor and on the microalgae production, and we create a number of sensor solutions. Nutrient sensing, uh, biochemical sensing, biomass, and process parameter sensing, as you can see on this slide. You see these different types of quantities that need to be measured, and the solutions we create consist of photonic sensing, spectroscopic in the UV to the near infrared, as well as imaging solutions, as well as biochemical sensor innovations. We try to quickly move these early demonstrators in the lab or in line so we can see whether they already fulfill the need and the requirements. And as you can see, they are at the moment not tiny and not miniaturized because the first focus is getting them to work, proving their benefit and efficacy. And once we have these specifications clear, we can go to miniaturization, for example, by creating photonic integrated circuits. And that is particularly the case for deployment in these photobioreactors. Now, technology is a key ingredient as and part of the solution. Technology alone will not do the job. These sensors provide the data, and these data need to be fed into data analytics, particularly in models, digital twin models, to come up with closed loop control. And you see that here schematically. Thanks to digital twin model of a bioreactor, we can have far more efficient use of resources, better management of residues, and an overall more efficient use of the reactor time. This is one example where technology and AI will help us move towards Industry 5.0. If we switch now to Health 5.0, what does this mean? Well, this definitely means personalization as well as less human doctor intervention. Many may then ask, does this mean we no longer need doctors? Well, that's actually not the case. It does not make doctors less necessary. It frees important time so doctors can focus on new problems. And unfortunately, new problems keep arising. So overall, this is a win-win for the entire health ecosystem. You may not be aware of it, but in terms of health, a bad diet is said to be worse than drugs, alcohol, and tobacco combined. Yet changing a bad diet into a good diet is extremely difficult. Changing people's behavior is extremely difficult. And because that is such a grand challenge, we devoted some time, experiments, and collaborations on studying eating behavior and particularly studying snacking behavior. Roughly 30 to 50% of the calories that we eat are coming from snacks, so in between meals, and only the remainder is linked to the actual meal. This makes it even more complicated because measuring the calories and the overall balance of your meal may be possible, but to track all that snacking And to change that into a healthier behavior means you need to do real world evidence, you need to do continuous monitoring, and so on. Smartphone apps have been created to help with this, yet they lack precision and accuracy. And we created what you see on the top right. We created a custom snack box able to include both solid snacks as well as liquids. And a number of people were followed, and they could use their own favorite snacks. And we followed them during a week and tried to predict when people would be snacking so that in a later stage we could give them healthier alternative suggestions. From the pure observation, we could already draw important conclusions. For example, the size of the package played a role, whether there's single cookies, multiple, and so on. Same with liquid, whether it was in a cup or glass versus in a container, and so on. That was already relevant information that could steer also food and beverage companies towards creating healthier alternatives. Now, we didn't stop there. We went further than that. We also probed people's stress and the link to snacking. And we found truly outspoken gender differences in this study. In the study population, it turned out that men and women react very differently to stress. Men snack less when stressed, and women snack more. And this trend, as you see on the bottom right, was extremely clear in this entire group. Now, rather than generalizing that this is always correct, this does demonstrate that personalized and individual advice are really needed, and that's a Health 5.0 example and requirement. Now, focusing on food intake is one part of the puzzle, but it's also about what your body does with it. Now, Health 5.0, you may think, does not exist yet at all, and in this example, that is correct. But some of the oldest examples that exist, cardiovascular pacemakers, brain stimulators, and so on, are actually building on such innovations. And you see those examples here. They are quite old, over decades of evidence. Now, these are very powerful examples of less doctor-patient intervention, personalized and autonomous control. So these are fantastic examples of how patients can benefit from Health 5.0. Unfortunately, these examples are in the cardiovascular and neurological domain, and in almost all of the other areas of medicine, such Industry 4.0 or 5.0 examples are lacking, and particularly lacking when it comes to food, nutrition, and health, and gastrointestinal health. After all, our gastrointestinal tract is a black box. We start to pay more attention to what we eat. We definitely don't pay attention to what leaves the body, and we have no idea what happens in between. And there are no tools to help us with that. That is the main reason. It's not that we're not interested, tools don't exist. And gastrointestinal problems are not a small problem. They affect 1 in 4 people, and gastrointestinal disturbances are not limited to the gastrointestinal tract. They actually will have an effect on your metabolic health, on your immune health, and even on your mental health through the gut-brain axis. So it's an extremely important system in the body, yet it is a black box for us. And while we have wearable smartwatches for cardiovascular health, and they play an increasingly important role, we don't have anything similar to monitor gastrointestinal processes. And that is where Industry 4.0 can help, and new sensor innovations can help. What exists today are endoscopes, gastroscopes, obviously not a scalable solution for a consumer population or a patient population. We had in mind um, a vision of a small ingestible sensor that would follow and go through the entire GI tract and would monitor in real time, linked even to nutrition, to food, and so on, which is definitely not possible in any of the other techniques like endoscopy and so on. Furthermore, imaging solutions like shown on the left only will give you images, will not tell you anything about the metabolites, biochemical markers, the microbiome, disease markers like inflammation, and so on. And for that reason, we think such an ingestible sensor has an extremely large potential and can give real-time feedback to people and to patients and to professionals. Now, it was easier said than done. It took us over 5 years to go from a drawing of an ingestible sensor to the reality. We created an overall very small sensor, FDA size 0 capsule, that is easy to swallow. A team of 25 to 30 researchers created this, and it has a multitude, 7 different sensors, and electronic circuits, wireless communication, measuring and sending data wirelessly to a base unit and then to the cloud. We took it through the entire regulatory process, and we got regulatory approval end of 2023 and conducted studies in 2024. The first study was on healthy volunteers, and we followed 15 people with multiple sensor pills in that first study, where we already included certain diets, first their own diet, and then a control diet, and then again reference. So people swallowed different pills. All of them mentioned that it was easy to swallow. They would not mind contributing to a future study, were interested in the results, and the age was from 21, if I remember correctly, to the late 70s, and this was a very good first type of user feedback as well about acceptability of these devices. Now, to dive a little bit deeper, here you see the timeline of the last 4 or 5 years. We explored multiple form factors, different types of sensors. We had to do in vitro as well as in vivo validation, struggled with topics such as getting a compact yet efficient antenna for communication from the ingestible to the outside world. Low power operation had to be maintained so that we can have up to 2 weeks of battery life on these primary batteries. And then a lot of regulatory documentation, regulatory tests, and so on, before we got approval from the Medical Ethics Committee to conduct human studies. Now, that worked. And here you see some example trajectories of certain markers, a very obvious one as pH and a very not obvious one like redox potential linked to inflammation and other applications. As I indicated, we had 15 volunteers with an age up to indeed 79 years of age. Every participant swallowed 4 ingestibles at different moments. The transit time varied strongly from person to person, varies also with your diet. That alone is a relevant quantity that many doctors are interested in, but you get a lot more information from this entire mapping of the GI tract over multiple days. And the diet, just to tell you a little bit about the diet interventions, This was greatly helped by the team of nutrition experts at Wageningen University, making sure that volunteers followed these specific diets. You see the preparation so that we could be sure that every single candidate had the same identical diet during the entire week. And you see that here. Here you see a larger version of that ingestible. One of the challenges is to make sure that these sensors survive the harsh environment of the stomach, because there the pH is the lowest and the sensors are at most risk for failing. So the gastrointestinal tract is a rather harsh environment, and making sure sensor innovations survive is a challenge. Unlike imaging solutions, where you could enclose and encapsulate the sensor and shield it hermetically from the harsh environment, with chemical sensors, you don't have that option. So making sure we have robust sensors throughout the GI tract was one of the large challenges we focused on. Now, because of regulatory approval, we even used this sensor live at a large event, where the project leader swallowed the sensor pill in front of a few thousand attendees so they could see the real-time data. This is shown here.
But yeah, let's go for it.
So while you may say this is a bit of a gimmick to have somebody ingest a sensor, this was of course important to show that we have indeed real-time data, and you can see the important changes as soon as the sensor goes from esophagus into the stomach and then moves from stomach to small intestine. And you can see these strong changes in sensor data to indicate that we have real-time information. Today, this is open loop, but keeping Industry 4.0 and 5.0 in mind, this lends itself to closed loop feedback and control systems. Also here, technology is important and essential, chip technology, to create a sensor. This requires also digital twin models of the gut, a gut model which helps in terms of localization of the ingestible, which helps into combining the data from different sensors on the same person, as you see here, because while the time may be different, synchronization can be conducted, and you see that here, how data then starts to coincide. The aspect of data analytics and gut health models is really essential because raw data is insufficient. I mentioned briefly localization. So although the sensors enable some type of localization, we also created sensor technology to do localization with an approximate accuracy of 2 centimeters, which will definitely be helpful when deploying the sensors, in particular patient populations, such as patients with inflammation, where localization is critical. When it comes to nutrition and health, it's more about the chemical data, and the local variation will be far less. Now, apart from sensing solutions, we are also creating sampling solutions. And you see here a sensor-guided sampling pill, which at a given moment inside the small intestine or at a certain location in the colon, it will sample microbiome for offline analyses. After all, our microbiome plays such a big role in our health and in many human body processes, yet that is also a black box at the individual level. And we aim to change that by creating such innovations. Now, sampling a microbiome for offline analysis does not sound comfortable, and you are correct. Retrieving this capsule is something you can do in a research stage, patient studies, and so on. This would never be usable by consumers. For that reason, we are focusing our R&D on a microbiome activity sensor, which does the analysis inside the ingestible sensor itself. That, we believe, has the potential to really bring this microbiome monitoring to a large population and in the frame brings it to the framework of health rather than disease alone. As a completely out of the box future scheme, we are also looking at other sensing modalities and concepts. As I indicated, keeping a sensor alive is a challenge, and we look therefore at bio-inspired sensing. And we call them living biosensors, where a combination of bacteria that are used as the actual sensor and transducers that are fluorescence based, for example, together make far more powerful and robust sensors. This type of innovation um, combines synthetic biology and electronics and is something that we think has a lot of potential, combining bioware with hardware and with AI together. However, this is also something that is easier to draw on a slide than turn to reality. We think this will keep us busy for the next 5 years before we have truly powerful and usable concepts that can be used in vivo. Let me finally give an example of Agriculture 5.0. Today, a lot of the knowledge is still in the head of the individual and aging farmer. And for that reason is more an Agriculture 3.0 example and maybe 4.0 in controlled environments such as a greenhouse where IoT devices can be deployed. Very often, or rather almost everywhere, the, the knowledge is truly qualitative through experience of these farmers. It's very powerful, yet how can you make this scalable with a shrinking amount of farmers? How could you translate this into robot harvesters or autonomous growing solutions? That's still a massive challenge. And this needs a number of sensors. This needs digital twins of the greenhouse or digital twins of an orchard and so on. And it's a formidable multi-partner collaboration and challenge that we aim to tackle. And the challenge is made larger by the fact that these are low to medium volume markets. These are not domains that need hundreds of millions of sensors like mobility, communication, and so on. This will be a far lower number of sensors that are needed. And for that reason, it is a big challenge to make it cost effective, to create cost effective solutions. To solve that, and to solve the cost of ownership, we really focus on only one platform technology. We focus on integrated photonics because that is more broadly usable. The technology platform is created for other markets, for other applications. We're using LiDAR, for example, which is deployed for automotive. So then building on that technology for agriculture makes a lot of economic sense, because otherwise you end up with a great solution, yet it is too expensive to be deployed. Similarly, We are creating tunable diode laser-based absorption spectroscopic solutions using integrated photonics. These platforms are also usable for certain health monitoring applications. So also here we have a larger potential volume and which can make these solutions more affordable as needed by these markets. And here you see an example of an orchard that was measured, analyzed, classified with convolutional neural networks using LiDAR data. And you see indeed the trees, you see branches that were clipped, and we fed that into an overall digital twin of the orchard and added both a robot and a digital model of the robot to teach the robot how pruning and clipping should be done. And you see that example here, both in the digital version as well as a real version. And the benefit, of course, is that when doing this in a virtual reality environment, you can make mistakes and try out. And for that reason, we have also created a virtual reality package so that people can try it out themselves and seasonal workers can learn how this should be done rather than trying these processes out on the actual trees immediately. Now, this was just one example of Agriculture 5.0. As I indicated, Agriculture 5.0 will also need environmental sustainability. This is also a domain where sensing of the environment, air, water, soil, is essential. Also in this domain, we focus on integrated photonic solutions, and you see here an example of Vernier laser for spectroscopy of gas sensing in the barn and in the field, and an example of a first breadboard system deployed in a barn is shown here. It's time to conclude. With these different examples, I hope that I shared with you both my enthusiasm and as well as the potential and the need for Industry 4.0 and 5.0 solutions in these specific areas of industry, namely agriculture, food, and health. I think with these technologies, we really have the potential to work towards sustainable health, sustainable food, sustainable agriculture, and that is what our planet needs in the coming decades. Thank you.